So here's section 7.2. In this one, we're going to talk about how to estimate the value of a population proportion. And when we're talking about a population parameter, that would mean, in this case, the proportion for the whole population. If we're going to estimate that, the way we can do that is to select a sample and look at the proportion from that sample. And that's going to give us the best estimate, one number estimate of our population proportion. And we call this one number estimate a point estimate. So we can use our proportion from our sample to construct a confidence interval. And this is a range of values that go on either side of our point estimate. We're going to use that to estimate the true value of our population proportion. So we're going to talk about how to construct confidence intervals and then how to interpret them. The other thing we should know is how to find what sample size we need to get a good estimate of a population proportion. So here again, a point estimate is just a single value. That's why we call it a point estimate, because it's just one point. We use it to estimate a population parameter, like a proportion. When we're talking about proportions, the best point estimate of our population proportion is our sample proportion. Here's an example. In a poll, 70% of 1,501 randomly selected adults in the United States believe in global warming. Our sample proportion is the proportion of adults that said they believed in global warming from our poll. So that would be 70%, or in decimal form, 0.70. Now we want to find the best point estimate of our proportion of all adults in the United States who believe in global warming. So we're trying to find a point estimate of the population proportion. And that's just going to be our sample proportion. So our sample proportion, the 0.70, is our best point estimate of our population proportion. If we had to just give one number that we said we thought was a good estimate of how many adults in the United States believe in global warming, we'd say 0.70 or 70%. Now the problem with just using a point estimate is that depending on what sample you pick, if you get kind of an unusual sample, then your point estimate might be off by a little bit. So instead of just using that one point, what we like to do in statistics is use a whole interval of values, or a whole range of values. We call this a confidence interval. When we use a confidence interval, we have something called the confidence level, and this tells us how certain we are of our numbers, how confident we are in our estimate. The most common choices for a confidence level are 90%, 95%, or 99%. So what you'll see a lot of times in the news, if they're talking about a poll that was done, they'll say 95% confidence. That's what they're talking about. And what we're going to do is use the confidence level to find another value that we call alpha. And this is something that we're going to use quite a bit. So like for instance here, where our confidence level is 90%, alpha is just going to be 100% minus that. So if the confidence level is 90%, then alpha is 10%. If the confidence level is 95%, then alpha is 5%. And here, if the confidence level is 99%, then alpha is 1%. So the question now is, how do we interpret a confidence interval? What does it mean? So here we have a confidence interval. And again, this is just a range of values for a proportion. So it goes from 0.677 to 0.723. And let's look at just what this would look like on a number line. So if we have the 0.677 and the 0.723, what the confidence interval says is that our true population proportion could be anywhere in between these two values. And notice that these are open-ended, so it doesn't actually include either one of those two endpoints. But our population proportion could be anywhere in between those two. Now what the confidence level tells us is that we're 95% confident that this interval actually does contain the true population proportion. Now the way I like to think about this is that if we selected a whole bunch of different samples, So if we had the money and the time to go out and select as many different samples as we could of the same size, and if we made a confidence interval from each one, then the 95% confidence means that 95% of those intervals would actually contain our true population proportion. I like to call those hits, and then the other 5% would not contain the true population proportion. So those ones would be misses. That's the general idea of this. So here's a picture of something like this. In this one, we've got samples of size 50, if you see up here at the very top. So here's our sample size. And in this one, they used a pi for the proportion. So what they're saying here is that the actual population proportion is 0.5. So that's the p. There's a 95% confidence level here. So what this little app did is it just went through and did 25 random samples and constructed a confidence interval from each one. And so you can see we have all these confidence intervals, and all these ones that are in green were actually hits on the true population proportion, which is right here in the middle. So out of those 25, 24 were hits. And that actually gives us 96% that were hits. Now the one down here in red, notice that it doesn't cover our true population proportion. It's off to the side here. So it's a miss. So out of the 25, one of them was a miss, which is in this case actually 4%. But it's pretty close to our 95%. And that's the basic idea here. Here's another picture. This time we still have a sample size of 50. Our P in this one is 0.37. So that's where this is, this dotted line going down. Our confidence level is 90% here. So, and in this one I had it construct 100 confidence intervals, although it only shows you the last 25 of them. But look at these ones in red that are all misses because they're not hitting on what the true population proportion is. And it turned out in this case that it ended up being exactly 90% that were hits, because it turned out being 90 out of 100 that hit the population proportion and 10 out of 100 didn't. Okay, now we're going to talk about how to actually construct a confidence interval. So first of all, we need what we call critical values. For this part, we're going to get these from the normal distribution, so from the z-scores table. So what we're going to do is take our value of alpha, which remember is related to our confidence level. We're going to divide that in half, and we're going to say half of it is in each tail of our normal distribution. So this is going to be a value over here. Half of alpha is this area here. The other half of alpha is this area here. And then what we want to know is what's the value of z right here? That's the cutoff value. And remember, our normal distribution is symmetric, so this value over here will just be the opposite. So this will be negative z of alpha over 2. All right, so here's how we're going to find this. First, we figure out what our alpha is. If our confidence level is 95%, that tells us that alpha is going to equal 100% minus that. So alpha is going to equal 5%. We want to change that to a decimal form. So we're going to rewrite that as 0.05. Then we're going to divide it in half so that we have half in each tail. So we're going to take alpha and divide by 2. That gives us 0.025. So we know the area in each tail here is 0.025. Now, to actually find the z-score that goes with this, the easiest way and the quickest way, either with your table or with your calculator, is to use the one in the left tail. Because remember, when we're dealing with our z-scores table, we always have to go to the left. This one is already going to the left, so it's easier to just look up this. So what we need to do is look up our 0.025 in the middle of the table. So I'm going to write that as 0.0250. What that's going to give us is a negative value. So that's going to give us, if we look that up, the value that's closest to that is going to give us a z-score of negative 1.96. Now all we have to do is just take off the negative. That's going to give us our critical value of 1.96. And if you're using your calculator, you're going to do inverse norm. And again, if you just put in the 0.025 and 0 and 1, since we are talking about a standard normal distribution, this is going to give you a negative value, approximately negative 1.96. And all you do is take off the negative again. All right, now the other thing that we need to know when we're talking about our confidence interval, we're going to have our point estimate. And just like those confidence intervals that we saw in the app, our point estimate is going to be exactly in the middle of our confidence interval. And then we're going to go a certain distance on either side of that value. So here's our point estimate in the middle, and then what we need to know is how far we go on either side. And this value, this distance, is going to be E, which is our margin of error. We're going to find that with a formula. So here's our formula if we're finding confidence intervals for proportions. And here's the critical value that we already found. So that's part of this formula. The P with the little hat is our sample proportion. Q with the hat is just 1 minus P hat. And remember, these have to be in decimal form. So these two have to be in decimal form for this to work. And N is just our sample size. There are some conditions for this to work. Basically, we have to have something that comes from a binomial distribution. So don't worry about this too much. Just remember that there have to be only two possible outcomes, like yes and no, approve, don't approve, something like that. And that there have to be at least 5 successes and 5 failures for this to work. All right, once we have our point estimate, then we're going to use it to write our confidence interval. So our point estimate is always going to be in the middle, and then we're going to go the distance of the margin of error on either side. So we're going to take our point estimate and subtract our margin of error to get our lower limit. We're going to take our point estimate and add our margin of error to get our upper limit. And here are actually 3 different ways that you can write your confidence interval. You can write it as an inequality like this. You can just simply write the point estimate and then say plus or minus and whatever your margin of error is. Or you can write it in interval notation. So this would be your lower limit, just like in the inequality up here. And this one would be your upper limit, just like we have in the inequality up here. Just that this is written as an interval instead of as an inequality. And the round-off rule, if we're doing proportions, is that we're going to round our confidence interval limits to 3 significant digits. So when we go to construct a confidence interval, first we do want to verify that the conditions are satisfied. And again, the most important one of those is that there are at least 5 successes and 5 failures. Then we want to find our critical value that goes with our confidence level. Then we have to find our margin of error. And then we take our point estimate, which is our sample proportion, and subtract the margin of error to get our lower confidence limit and add it to get our upper confidence limit. And we round those values to 3 significant digits, and that gives us our confidence interval. So let's do an example. This goes back to our poll about global warming. We have a sample size of 1,501, and our sample proportion was the 0.70. So first we're going to find our margin of error. Well, actually before that we're going through and checking the requirements. And again, the most important part of this is that number of successes and failures. If we had 1,501 people that were polled, 70% is going to give us much more than 5 successes and many more than 5 failures, so we're fine there. So now we're going to use our formula to find the margin of error. And since this was a 95% confidence interval, we actually already found our critical value back in the example that we did. That was 1.96. And here we're putting in our sample proportion of the 0.70, remember in decimal form. The Q hat is 1 minus P hat, so that's where that came from. So that's just 1 minus 0.70. Here's our sample size. And remember, when you're doing this, you have to multiply these two and divide before you use the square root. Otherwise, you won't get the correct answer. So it would be a good idea to put this all in your calculator and make sure that you come out with the same answer that we have here. All right, so now we're going to construct our confidence interval by taking our point estimate and subtracting and then adding the margin of error. Our point estimate was the 0.70, so we're going to subtract our margin of error for this limit, and we're going to add our margin of error for our upper limit. And that gives us, once we round to 3 decimal places, that gives us these 2 limits. So again, we could also write this in interval form. So we could write it like this. And you will sometimes see confidence intervals just written as the point estimate plus or minus the margin of error. So you could also see it written like this. Now to interpret it, what this would say is that we're 95% confident that the actual proportion of adults who believe in global warming is between the 2 limits, the 0.677 and 0.723. If you're looking at polls that have already been done, just remember that for this to work, the sample should be a simple random sample. Can't be something like a voluntary response sample because that doesn't give valid results. They should provide the confidence level. They should provide the sample size. And the other thing to remember is that the validity of the results depends on the sampling method and the size of the sample, but it doesn't really matter how big the population is in comparison to the sample. That's a very common misconception in statistics. So if you just think about, say, Gallup polls that usually use a sample size of around 1,000, and those are used to represent the whole population of the United States, which is almost 300 million. So this is a very small number in comparison to the population size, but that doesn't mean that these samples aren't valid. They are valid because of the way they're selected. They're selected very carefully so that they're representative of the population. But the question we do have to ask is, what is the minimum sample size we need to make our results valid? So we're going to have 2 different formulas for this, depending on whether we have an estimate. And again, this is before we actually would do the poll or the survey or the study. If we have an idea beforehand of what the sample proportion might be, then we would use this formula to find the sample size. So notice that we still have our critical value, so we would have to know our confidence level. in order to find that. This would be, the p hat here would be the estimate of our sample proportion. The q hat would again just be 1 minus that. And the e down here is our desired margin of error. So for example, if we want our margin of error to be something like 3 percentage points, that's fairly common, then that's the number that we would use in here. And it does have to be in decimal form. So those two things are very important there about the E in this formula. Now, if we don't have any idea of what the sample proportion might be, then this is our kind of worst case scenario formula. If we don't have an idea, then we assume that the worst case, which would be that our sample proportion is 0.5. And if you put that in here, you get a 0.25 here instead of the p hat and the q hat. So this one works the same way, just that we use the 0.25 here. And we're always going to round our sample size up to the next larger whole number. Here's an example. In this one, a manager for eBay wants to determine the current percentage of U.S. adults who now use the internet. He wants to know ahead of time how many adults to survey in order to be 95% confident that the sample percentage is in error by no more than 3 percentage points. So we've got two different problems here. One of them, we have an estimate for our sample proportion from a prior survey. So that's the 73% here. And in the second problem, we don't have an estimate. So we're going to do this one both ways. So in the first one, we're going to use our formula with the p hat from our estimate and figure out the q hat from that by subtracting from 1. Our confidence level, we want it to be 95%, so that means alpha is 0.05, and we already have our critical value that we figured out earlier. And we said 3 percentage points for the margin of error, so this is just converting that to a decimal. So this is a way that this is commonly described as being in terms of percentage points. All right, so if we put all those numbers into the formula, notice that we're taking our critical value and squaring it, we're taking our margin of error and squaring it, we're multiplying the p hat and the q hat together, and so be careful and use the correct order of operations here. You have to do the squaring first before you multiply or divide. So this gives us an answer of 841.3, and remember, we have to round this up. For sample sizes, we're always going to round up. So that means the minimum sample size we could have to get a valid result from this would be 842. All right, now the second part of this problem was if we didn't have an estimate for the sample proportion. We still have our critical value and we still have our margin of error that we wanted to be 3 percentage points. Now we're using this formula with the 0.25 in it though. So we're putting in our critical value and our margin of error, and again just use the right order of operations. And for this one, like I said, this is kind of our worst case scenario, so the sample size is going to come out bigger. And again, we're rounding up, so we're going from 1067.1 to 1068, so that's our minimum sample size that we could use. Now when we get sample sizes like this, you can always use a bigger sample size than what your minimum is, but this is just the very least that you could have in your sample in order to get the margin of error that you want. If we're given a confidence interval, you can actually use the upper and lower limits of the confidence interval to go back and figure out what the sample proportion and the margin of error were. And for this, you just have to remember what your confidence interval looks like. And that is that your sample proportion is going to be right in the middle. So it's exactly halfway between the upper and the lower limits. And then the distance from either one of those limits to your sample proportion is just your margin of error. So if all you have is the two limits, then all you do is average them because the sample proportion is halfway between. So you just take the two limits, add them together, and divide by 2. Then once you have that, all you have to do is figure out how far it is from that sample proportion to either one of these endpoints. So really, this is one way to do it, the formula that's down here. But another way to do it is just take your sample proportion and subtract one of your confidence interval limits, and that'll give you the distance between the two. And that's your margin of error.
Now we're going to talk about a different population parameter, which is a mean, and we're going to talk about how to find point estimates and confidence intervals for those. Now, in order to deal with a population mean, we have to use a slightly different distribution. So in this section, we won't be using the normal distribution. We'll be using a different one, which is very similar, but it's called a t-distribution. So what we're going to try and do here is estimate a population mean. And again, we're going to find a point estimate, and the best point estimate for the population mean is going to be the mean from a sample that we've selected, so the sample mean. Since we already know how to do confidence intervals in general, we're going to go straight to the formula here. So again, we're going to be using our point estimate and our margin of error to construct our confidence interval. And here's the formula for our margin of error. And notice that here, instead of z for our critical value, we have a t, and that tells us that we're going to be using that t distribution. So we're going to be using a table from the book that has to do with the t distribution. And notice also here that we've got an S. This is our sample standard deviation. So that comes from the sample, and then the N is our sample size. And we'll talk a little bit later about how to use the table to get our critical value from the t-distribution. But one of the things that we have to know in order to use that table is what we call the degrees of freedom. And that's simple to figure out. It's just n-1, where n is the sample size. So some other notation here that we've got: mu stands for the population mean, x with the bar over it stands for the sample mean, or the mean from our sample, s is our standard deviation from our sample, n is our sample size, e is our margin of error, and t of alpha over 2 is our critical value from the t-distribution. And we construct our confidence interval the same way as we did with proportions. That is, that we take our point estimate, which in this case is our sample mean, x bar, and once we've found our margin of error, we subtract that to get our lower limit, and we add it to get our upper limit. And here's that formula again for our margin of error. So here are all the steps that we need to go through. First, we're going to verify that our requirements are satisfied, and those are pretty simple for this. Then we'll find our critical value from our t-table. We use that in our sample data to find our margin of error. And then we construct our confidence interval using our point estimate, which is our sample mean, and our margin of error. Then at the end, we'll round our confidence interval limits. Here's an example. In this one, we're looking at a claim that garlic lowers cholesterol levels. We had 49 subjects that were treated with doses of garlic, so the 49 is going to be our sample size, and their cholesterol levels were measured before and after the treatment, so the data that we have is actually the change in their cholesterol level. So the changes in their levels had a mean of 0.4 and a standard deviation of 21.0. So this is our sample data. So we've got n is equal to 49, our sample mean is 0.4, and our sample standard deviation is 21. We're going to construct a 95% confidence interval. So first we're checking our requirements. All we have to have for these kind of confidence intervals are that we had a simple random sample, and either that the sample size is bigger than 30 or the original population was normally distributed. In this case, we've got definitely that n is greater than 30, so that's the only requirement we need. Okay, now to find our critical value, here again we have to find alpha. For some reason that came out as an A instead of an alpha. But again, to find this, we're just taking 100% and subtracting our confidence level. In this case, that gives us 5%, which we write as 0.05. So we need to know the alpha, and then we need the degrees of freedom. And again, that's just n minus 1. So our degrees of freedom for this one would be 48. Now what you'll find in the t-table, if you look at it, is there's a part at the top that says area in two tails. That's the part that we're always going to use for confidence intervals, because we're always dividing our alpha between the two tails, just like we did with the normal distribution. So at the top, where it says area in two tails, under that you're going to look for your alpha. So the column you want to look in is the area in two tails where it has 0.05. Then to select the correct row, that's where you need the degrees of freedom. So you're going to go down to the one that's closest to the degrees of freedom you have, because this table won't have every value. It doesn't have a 48, so the closest one you'll find will be 50. So go down to the row that says 50 degrees of freedom, and where that row and that column intersect, you'll find the value of 2.009. So that's your critical value. Now we have everything that we need to find our margin of error. And again, the notation here turned out a little bit wrong. This should be an S. So we have our critical value of 2.009, our S, which was 21.0, our sample size, which was 49, and if we put that in our calculator correctly, we get a margin of error of 6.027. Now to actually construct the confidence interval, again we're using our point estimate, which was the 0.4, and our margin of error. So we're going to subtract the margin of error to get our lower limit right here. We'll add it to get our upper limit, and then for these confidence intervals, we want to round our limits to the same number of decimal places that our sample data was rounded to. So since our sample mean went to 1 decimal place, then we're going to round our limits to 1 decimal place also. So both of those need to match. But what this tells us, because our confidence interval actually has a negative number for a lower limit and a positive number for an upper limit, that means again that our population mean could be anywhere in between those two. Since 0 is in between those two, what that means is that the population mean for the changes in the cholesterol could actually be 0. And that suggests to us that the garlic treatment probably is not effective. Now again, just like we did with our confidence intervals for proportions, if we're given the values, the limits for the confidence interval, we can use those to find our point estimate and our margin of error. And again, remember what our confidence interval looks like. In this case, we've got the sample mean right in the middle, since that's our point estimate, and then on either side we go a distance of the margin of error to get to our limits. The point estimate is actually exactly halfway between the two limits, and that means if we know the two limits, we can just find the average. So we just add them together and divide by 2. Then once we have that, our margin of error is just the distance between our point estimate and either one of our limits. So we can subtract one from the other and get that value.